Welcome to the AI Research Roundup. I am Alex. Today, we're looking at a paper from May 22nd, 2025, titled AudioTrust, Benchmarking the Multifaceted Trustworthiness of Audio Large Language Models. Essentially, this research introduces the first comprehensive framework and benchmark called AudioTrust, specifically designed to evaluate the trustworthiness of audio large language models, or ALLMs. These are AI models that work with audio. The paper highlights that existing evaluations mostly focus on text or limited safety aspects, not the unique risks in audio. AudioTrust assesses these audio large language models across 6 key dimensions like fairness, safety, and even hallucination, which is when a model confidently states something false. And for those interested in digging deeper into how these audio large language models are evaluated, the authors have also shared their implementation. So the AudioTrust repository on GitHub provides everything you need to run the benchmark. You'll find the core evaluation engine, scripts for each task, and of course, the dataset descriptions to get started. This benchmark uses several specific tasks to test these models. Alright, and really brings AudioTrust's mission to life. It visually lays out these 6 key trustworthiness dimensions. For example, fairness tests if the model shows bias, say in evaluating job candidates based on their voice. Hallucination, which we mentioned, checks if the model invents details not present in the audio. Safety assesses if the model can be tricked into harmful actions. Privacy looks at whether models leak sensitive information, like a bank account number. Robustness evaluates performance with noisy audio, and authentication tests if the model can be fooled by fake voices. Okay, so building on that, offers a deeper look. Part A on the left again outlines those 6 core trustworthiness dimensions, but importantly, it further divides them into 26 specific subcategories for a more detailed assessment. Then, Part B shows a preliminary leaderboard. This leaderboard ranks 9 different audio large language models, both open source and closed source, like GPT-4o audio, on these dimensions. For some metrics, like fairness, a lower score is better. For example, the group unfairness score, or gamma, aims for 0. For others, like safety, a higher score indicates better performance. So moving to, this gives us a closer look at those group unfairness scores we talked about, specifically for social stereotypes and for decision-making scenarios. Remember, a lower score here means better fairness, with 0 being the ideal. And while the results show that no audio large language model is perfectly fair yet. Interestingly, open source models tend to show a bit more bias in stereotype situations, while some closed source models struggle more with fairness in decision-making tasks. For instance, Mini CPMO 2.6 performs quite well among the open source models, and GPT-4o audio generally shows strong fairness among the closed source options. Okay. So shifting gears from fairness, here delves into another critical area, hallucination. This is when the audio large language model essentially makes things up or gets details wrong about the audio. The table shows accuracy scores for different types of hallucination scenarios. We have content mismatch, or CM, which tests if the model's understanding of the audio aligns with a given textual description. Then there's label mismatch, or LM, checking for confusion with assigned labels. Logical violation, or LV, which sees if the model spots acoustically illogical events, and physical violation, or PV, likely looking for inconsistencies with plausible physical events or properties in the audio. And while the results show quite a variance, generally, closed-source models like Gemini 2.5 Pro and Gemini 1.5 Pro tend to perform better, meaning they hallucinate less. In contrast, some open-source models like Salmon show lower accuracy, suggesting they're more prone to these kinds of errors. Alright, so after looking at how models can go wrong with hallucination, shifts our focus to safety. This table presents the overall safety results using a key metric called defense success rate, or DSR. A higher defense success rate, which is what we want, indicates the model is better at resisting jailbreak attempts across enterprise, financial, and medical scenarios, and also better at avoiding guidance for illegal activities. Generally, closed-source models, like Gemini 2.5 Flash, show stronger defenses. Open source models, conversely, appear more vulnerable to these attacks, particularly in those jailbreak scenarios. Okay, so we've talked about safety. Now let's turn to another crucial aspect, which is privacy. Here shows us the aggregated privacy leakage refusal rate scores. Essentially, a higher score means the model is better at refusing to leak private information. The table looks at two types of leakage. Direct leakage, which is explicit information like bank accounts or social security numbers, and inference leakage, where the model might deduce private details like age or ethnicity. It also compares performance with and without augmentation, which refers to using privacy-aware prompt engineering. And the results are quite mixed. For very sensitive data like social security numbers, some models like GPT-4o Audio achieve a 100% refusal rate. However, for things like home addresses, some models, particularly in the Gemini series, showed complete leakage without that prompt engineering. Interestingly, this prompt engineering significantly boosts protection against direct leakage, but it's less effective for preventing inference leakage. And among open source models, Ultravox shows strong performance in direct privacy protection when prompts are used. So after looking at privacy, moves us to another really important aspect: robustness. This table shows us the accuracy of these audio large language models under different challenging conditions. We're looking at how well they stand up to things like adversarial robustness, or AR, which are inputs designed to trick the model. Audio quality variation, or AQV, so how they handle degraded audio, and noise interference, or NI, which is pretty self-explanatory. And well, there's a clear performance gap. The leading closed-source models, like Gemini 2.5 Pro and Gemini 1.5 Pro, generally do much better across these tough scenarios. They're more consistent when faced with background noise, multiple speakers, or poor audio quality. Among the open-source models, Mini CPM-O 2.6 shows some notable robustness, but overall, the closed-source options seem more resilient. Looking at these robustness results, and considering the privacy aspects we discussed earlier, it is clear that AudioTrust provides a vital benchmark. It highlights that while audio large language models are advancing rapidly, their trustworthiness, especially in areas like privacy and handling noisy inputs, still needs significant work. This research really paves the way for developing more reliable and secure audio AI. That is all for this AI Research Roundup. Thanks for tuning in. I am Alex.